Hi, welcome back. I'm Greg Smith, aka Dr. FreeRTOS, and today we're going to look at programming. Now, I'm working on my iBookintosh project, and it's time to write code. And I don't want to use Python; it's too slow for this project. And I don't want to use C++; it's too bulky. So that leaves me with C. So today we're going to look at object-oriented programming in C on Dr. FreeRTOS. So before we get started, let's talk about what is object-oriented programming. So let's go to the magic whiteboard and take a look. So there are three parts to object-oriented programming. The first part is encapsulation. This is the ability of an object to have all of its elements inside that object and contained or encapsulated within that object. The second part of OOP is inheritance. So this is the ability to take an existing object or an existing class and borrow from or inherit from that class to create a new class. So for example, if you have a general class of shape, you might want to have square, circle, triangle as different classes of shape, and you want that those classes to all inherit from the general class of shape. And finally is polymorphism. This is the ability of an object to be treated like some other object. So, for example, if you have an object, let's say, of dog, and then you have collie, and you have also a Great Dane, then you would want to be able to have the collie kind of act as if it were a Great Dane, or more specifically, that the collie and the Great Dane are both treated as if they were a dog, and you don't know when you're working on them that they're of a specific type. So those are the three parts: encapsulation, inheritance, and polymorphism. There is another one that some people add, which is abstraction. We're not going to talk about that today, but in my mind, the other three elements of object-oriented programming already give you abstraction, so we won't need that. So let's go to the IDE, and let's start writing some code, and let's take a look at how we would normally write some code that would be let's say our task manager in the iBookintosh project, and see how we would implement that with straight C code. And then we'll start adding on and giving these different elements and seeing how we can create encapsulation, inheritance, and polymorphism. So what we're going to do is start with the classic blink program and try to blink multiple LEDs at different rates. And the first thing we'll do is we'll blink one bulb to remind us how this program works. The second thing we'll do is blink two LEDs, and that will show the problem with this approach. Then we'll try to blink four LEDs with the same result, and then we'll start breaking this down so that we can blink four LEDs at different rates. So here we have the classic hello world of the microprocessor world, which is the blink program. So we set the board LED, the state of the LED, how long we want the LED to delay, and then down here in our main code, we initialize the LED, and then we loop forever. We call blink LED with the current LED, the amount of time to delay, and the current state of the LED. And the idea here is that we pass in a 0, it waits until a certain amount of time has gone by, changes the LED from 0 to 1, and then returns that new value to update the state, so it constantly blinks. So here's the LED init function, which calls the GPIO init on the board LED, and then GPIO setdir to set the direction to output. The blink function takes an LED in, the amount of time to delay, and what the current state is. It delays by calling the sleep function for that period of time, sets the pin to the state that was passed in, and then returns the inverse state. So on the next iteration, it will go from high to low or from low to high. So let's go ahead and take a look at this program in action. You've seen this many times before, so it won't be anything new or surprising. All right, so now let's extend this program and let's try to blink two LEDs at different rates. And let's see what that looks like. So here's the blink 2 program. So we have the board LED and a red LED, a board state and a red state, the delay for the board LED and the delay for the red LED. In the initialization function, we call the GPIO on the board init, the same as we did last time on the board LED, and then the GPIO init on the red LED, and we set the direction to out. And the blink LED function is the same as last time. Then, as before, we initialize the LEDs, and then we call the blink LED on the board and the blink LED on the red, and we get this. So what you may see here is that while they are blinking at the same time, the red LED follows the board or LED, right? That the board LED comes on, and then followed by the red LED coming on, and then the board LED goes off, followed by the red LED going off. And what should be happening is that the board LED is blinking twice as fast as the red LED. But because we're pausing in our code using the sleep function, the red LED must wait for the timeout of the board LED. And that means that it can only follow. It can't blink at its own rate. So what's happening is that neither of them are blinking at the rate that I specified. The board LED and the red LED are both blinking at about 3/4 of a second apiece. And that's not what we're looking for. So that may not be obvious when you look at it with 2 LEDs. So let's do the same thing with 4 LEDs. We've got the board LED, red, green, and yellow. We've got red, green, yellow state, red, green, and yellow delay. And in this case, the board LED will be a 1/4 second delay. The red LED will be a 1/2 second. The green will be 1,000 milliseconds or 1 second. And the yellow delay will be 2,000 milliseconds or 2 seconds. As before, the LEDs are initialized and their directions are set. We haven't changed our blink function. And now we are going to initialize the LEDs. And then in our forever loop, we will call the board LED, the red LED, the green LED, and then finally the yellow LED, all of them to blink. And as you would expect, they don't blink at the rate that they were specified to blink. So here you can see that the LEDs are not flashing independently, that the yellow LED is actually holding up the other LEDs until it goes off, and then they can come on. The red LED then comes on, it times out, goes on to the yellow or to the green LED, and then the process starts over again. So we need these to be flashing independently. The red should be flashing twice as fast as the green twice as fast as the yellow, and the yellow about every 2 seconds. So let's see if we can't get that to work. So the first thing that I'd like to do, though, is come back to the idea that these LEDs have their code kind of sprinkled all throughout, and it does make it kind of hard to manage. You know, we have the setting of the constants up here at the top. We have the states here, the delays here, the initialization function in the middle, and then finally the execution at the bottom. So let's see if we can't encapsulate all the elements of a single blinking LED, because they're all very similar, right? They all have the same elements, and they all execute the same pieces of code. So let's see if we can't encapsulate all of that information into one thing. And the C programming language gives us that capability in what's called a struct, or structure. So here we have a struct. We're going to define the struct LED to be a pin, a state, and a delay. And I use typedef here so I don't have to constantly type struct. So we have a typedef called LED. And now inside the LED init function, we pass this struct in, and we can initialize a single LED. Likewise, when we create a new LED, we'll want to allocate memory for that LED, and then set the pin, the state, and the delay to that structure, and then call the init function on that LED, which comes up here and initializes the pin and sets it to an output. Next, we call the blink function, passing in the LED, and we sleep for whatever the delay is on that LED. We set the LED to the input state, and then finally we invert the state and return. The code now at the bottom here looks slightly better. We're initializing the LEDs as before, and now we blink them, and this does the same as it did before, but we've made our code more generic, right? All the elements of the LED are in one place, and that's the first step towards encapsulation. So let's look at what that looked like before. Here we have all the disparate elements of the LED in separate pieces of code. Here we have to initialize all the LEDs in one function. And here we have the function that blinks the LED. It takes the values in as parameters and just executes them. So we've done a little bit to make our code easier to manage by encapsulating the data into a structure. But we still haven't addressed the problem of making the LEDs blink independently. That's not something that object-oriented programming itself will solve, but it will make it a lot easier to address the issue. Let's look at that next. So now, while it's not strictly part of object-oriented programming, I would like to start to address this multitasking capability that I'm trying to build. And one of the reasons I want to use objects instead of strict C programming is that it makes it easier to iterate across tasks and not be concerned about the internals of the task. So in order to fix this particular problem, we're going to do everything pretty much the same, but I'm going to introduce a timer. So here is a function called now, which calls the pico time microsecond, and I'm going to divide it by 1,000 because I'm only interested in millisecond time. The next thing we're going to do is that in the blink method down here, we're going to call the now function, get the current time, and then check against the last time the LED blinked plus the delay. And if the current time is past that future time, then we want to do the blink operation. Otherwise, we're just going to return. So this is significant. We're not going to pause like we did here with the sleep function, but we're just going to check, is it time to blink the LED? And if it is time, we reset the last time that it was run, we invert the state of the LED, and then we set the LED to the state that we now want it to be in. Down here, this code all looks the same as it did before. This code all looks the same. Now there is one thing that I did change, and that I was added the last time member to this structure. So this is actually a pretty small change that allows us to create a more multitasking capability. And in this case, the task is to blink an LED at a particular rate without the other LEDs interfering. So let's see what that looks like. So we have success. You can see the board LED is flashing every quarter second. The red LED is flashing every half second. The green LED is flashing every second. And then the yellow LED is flashing every 2 seconds. So if this looks like a binary sequence, we have succeeded. Each of these LEDs flashes at its own rate without any interaction from the others. So this is a good start. However, I'm still not satisfied. One of the challenges that we have here is that in order to call these functions, these methods on these objects, we have to know what methods are available, and they really should be part of the method or part of the object itself. So the next step is to actually pull these functions into the structure and make it part of the structure itself. So if you look here at our LED structure, we still have our pin, state, and delay, and the last time it ran, but here's this new syntax that says here's a pointer to a function and it takes as input an LED. Here's another pointer to a function called blink that takes as input an LED. These functions down here have not changed, but now the init function adds in the initialization of these functions. And so when we create our LEDs, you can now see that we can call the blink function directly. So we can say, board LED, I want you to blink. Red LED, I want you to blink, and so on. So while this may be a certain amount of syntactic sugar, it actually has some other powers as well, in that if we wanted to, we could redirect the red blink function to some other function than the others have. And that gives us a capability of eventually having some amount of polymorphism and later inheritance. So we made a very small change. We now have our methods, as they're called in object-oriented parlance, built into or encapsulated in our object, and that makes this a much easier piece of code to read. Now there is a problem, and that is that while we are using the LED object to call the blink method, we have to again tell the blink method which LED we want to blink, and this is a little bit of a downside. It's syntactically ugly, and it is not very object-oriented. What we really want is to be able to just call the blink method and have it know that we are calling it from the board LED or the red LED. Now, the C programming language doesn't give us this capability, but what we might be able to do is create a global variable that we assign the current object to and call the blink method with that. So let's take a look at what that might look like. So we can say this global variable, this, capital this, is equal to the board LED, and then we say this blink. Okay, and then we might do the same thing with red, green, and yellow. So what we can do now in the blink function is we say, hey, LED this is equal to capital this, the global this, right? And now we get that sort of object-oriented feel that current object that we're working on is the one that called us. So this syntax is pretty ugly, and up here you can see I've created my global variable. This syntax is pretty ugly, and we definitely don't want to keep this. So let's play another C trick and use the macro C preprocessor to assign a value to this just before we call any method. So I've created a macro here called call, for example, and then specify the object that we want to call. And then we use a little known feature of the C programming language that when you list a bunch of values or expressions inside of parentheses and separate them by commas, it will execute those expressions from left to right, and the last value or the last expression is returned as the value of that parenthesized list. And normally this has almost no value to us as C programmers, but in this case what we can do is we can surreptitiously set this to the object that we pass in, and finally return that object as the value of the thing that we want to call. So that would mean that down here all of this code turns to board LED blink. And this is a little bit of syntactic sugar that allows us to get an object-oriented feel to our code. So now when we run this code, it runs exactly as it did before. It gets the value of the board LED, assigns it to the global this value, and then calls the blink method. And when the blink method picks up, it gets the last thing that was assigned to this, and that becomes the this for this function. We are now able to perform this method as it was called from the object in question, from the LED object. So I particularly don't want to type out call every time I want to make a call, so I'm going to global change this to underscore. And now this is the final form of our object-oriented programming language in C. That anytime we want to call a method, we use underscore, the name of the object, and then the method we want to call, and we can pass any parameters we want without having to specify that we're calling a particular LED. So this is nice, but we still have a lot of code here on our main, and what we really want is for our LED to look like a class. And to do that, we need to take all of this code out, put it into its own C file, and then put the structure definition here into a header file. And that way the header file becomes the interface to our class, and the .c file becomes the implementation of our class. And this is very similar to the way that C++ works. So let's take a look at what that looks like. So here's the led.h file. It has our structure in it. It has all the include modules that we will need for using this object. And we've got our global variable, which is extern, for the this. And we've got our special syntactic sugar macro that allows us to make our method calls. And then the one method that we want to expose to the world is how to create a new LED. And in this case, we only pass in the pin and the delay. So now let's see what the implementation module looks like. Here's led.c. So we include led.h. It's the only thing we need to include. We need to create, instantiate this local this object for the LED so that when we call our methods that we can pick up the global value. Here's our now method. Here's the LED init method that we used earlier. It picks up the global variable and then using this assigns or initializes the pin, the output, and sets the current state. To blink, we get the global this. We check to see that we haven't surpassed the current time. If it hasn't passed yet, we return immediately, but if it has passed, we update the last time to the current time, we invert the state, and then we output the pin. And finally, if we want to create a new object, we allocate its memory, we set the pin, the state, the delay, and the last time being now. We also set our methods, and we immediately call the init method to initialize our LED, and then we return that LED. So this has very much encapsulated the LED capabilities into one source module. Everything having to do with blinking and LED is in one place. And if we ever want to change the way this works, we know exactly where to go. It's not spread out across our code. So what does our code look like now? So this is very straightforward. We initialize or create our new LEDs, the board, red, green, and yellow. Then we can iterate forever over each of the LEDs, asking it to blink. So this is a much more succinct and actually more readable way of programming individual objects within C. But there is one last thing that I'd like to do, and that is I really would like to be able to put these LEDs into an array and then iterate across them. And so here we have it. We create an array of LEDs, we set the number of LEDs to 0, and then we assign a new LED to the first element, and then we increment the index, and we do this 4 times, one for each of red, green, and blue. Notice that I haven't used the words red, green, or blue anywhere in here. And now I can iterate over those LEDs and tell each of them to blink at their rate. Whatever rate that they're at, they will blink. And now we have the very basic kernel of what will become our multitasking operating system. We can treat each task in our system as an object, and each task will have methods on it that we can operate on. And we don't need to know specifically how that task works because it'll be all encapsulated inside the class of that object or that task. Now let's go back for a minute and look at our original program and look at some of the differences. First, all of the information or the members of our object were spread across our code. We had to modify individually named pieces of an LED in order to update it. We had to initialize each of the LEDs independently. We had to stop doing everything. The processor could not do anything else while the LED was trying to blink. And then down here, when we created the LEDs, we had to blink them explicitly. We now have a more clean way of defining our LEDs, and our LEDs are encapsulated into one entity without our code being spread all over. So we've got a good start on our multitasking operating system, and we've got the beginnings of an object-oriented programming environment in C. Next, we need to add polymorphism and inheritance. As always, please don't subscribe to this channel. Don't like or click here. Your time is precious. You have so little of it. Thank you so much for spending part of it with me, and I'll see you next time on Dr. Frankentosh.